We love you guys, but we get tired too. Here we go, section 9.1. What should we fill on this page before we see if you guys got the example correct? Let's see. Sequence of events. When have you heard sequence of events before? Besides math. Chronological order, if you're talking about like maybe a storyline, right? Like a timeline of a story. What else? Sequence of events.
Mysteries.
Mysteries, yeah. Or like detective shows, things like that. They're trying to think of the sequence of events. They're trying to think of the timeline yet again. What was the order in which things occurred around a crime, etc., etc., etc. A sequence in math still has to kind of do with chronological. In the sense of this little term down here, which you might want to highlight if you're that kind of note taker. Nth term. It's something new, it's something different, something kind of complicated and yet sort of simple at the same time. A sub n is a notation for what we call the nth term. And as you guys realized in your calculator, SEQ, sequence mode, n is a very important variable because that's what the x turns into in sequence mode. Some of you might have gone to par mode and pole mode and figured out that x can stand for t and beta also. That's why there's 4 variables on your variable button. Anyway, coming back, now you're all checking it out. The nth term, what does nth mean? Some of you guys have heard like speakers before, whether motivational speakers or pastors or chapel speakers, maybe talked about to the nth degree. Maybe you didn't know what that meant before. The nth term, the nth degree, is talking about, well, as far as the nth term, we're talking about the place value. When n is 1, the first term. When n is 2, the second term. Now there is one slight change that might occur. That's why there's this little note down below. There might be times when n should start at 0 instead of 1. Let me just give you a quick, an illustration as to how this can happen. In physics, when we're talking about, or maybe not we as in us collectively, but when people are talking about at the beginning of a situation, of a scenario, of whatever motion or action is going on, at the beginning, what would they set time equal to if it's not some sort of specific 9 o'clock, 10 o'clock, whatever? At the beginning, they would say time is equal to 0.
So you know physics, you should teach it.
So, t equals 0. T equals 0 would be the beginning of a physics situation or a scenario or a model that we're trying to do. That is an example of when we might start at 0 instead of starting at 1. But with sequences, for the most part at this point, since we're not in Calc BC yet, what? Go team, they're doing sequences also. Actually, they've already done them. But anyway, coming back. Much harder. There is a time, possibly, when n can equal 0 or when n can equal 1. But the nice thing is, for our purposes, we will almost always try to start at 1. We will almost always try to start at 1. And the reason being, if you think about this nth term idea, doesn't it make more sense for the first term to be a sub 1? Does that make sense? Which term? First term. Wait! They're wrong. First has an ST and N has a TH. Why do they put N instead of N's?
What?
Doesn't N mean the placement? Why did they put TH if it's ST for first? Wait, what's the little superscript for second?
Second.
ND. How about third? RD. How about fourth? TH. How about fifth? TH. How about sixth? How about seventh? Why does it say N? It's TH for everything except for the, I don't know why we did. I mean, I guess the 1 sounds weird and the 2 sounds weird and the O2. Anyway, the 3 sounds weird, but 4th, 5th, 6th, 7th, 20th, 21st. Ooh, it goes back to ST. Anyway, the majority of terms will have a TH. Anyway, something random to think about. But it makes more sense for A sub 1 to be the first term. A sub 2 will be which term? Second. A sub 3 will be which term? Third. A sub 4, etc., etc. What's A sub n? I don't know, the nth, whatever position it's in. Okay? Vocab, terminology, introduction, let's keep going. So, what is this the formula for? What am I going to say as a math teacher when I read this? A sub n? Maybe, but what am I going to want to say? Nth term. So the nth term is given by the formula 3n minus 2. Who's n? The subscript, or the placement. in the sense of first, second, third, and fourth. So what did you guys do for a sub 1? Hopefully you plugged in 1. And when you plugged in 1, oops, plugged it in correctly, minus 2. Did you guys figure out the first term is 1?
Yeah.
Cool. The second term, when you plug in 2, did you figure out the second term should be?
4.
4? Cool. Did you figure out 7 and then you figured out 10? Whoa. Did I just do 2 different equations in my head? No, not even close. What did I do?
Memorize.
Nope, I figured out every time the 2 is still going to be subtracted, that stays constant. The only thing that changes from one term to another is multiplying in another 3, aka adding in another 3. So I was able to find more terms another way using a jumpity-jump-jump pattern. How to jump from one term to the next. So I could go ahead and you could go ahead, we could all go ahead and say, hey, what's going to be the 5th term using our jumpity-jump-jump pattern? Oops. If only I could add 13. Don't worry, it's not a math teacher. Okay. Anyway. Now what if I was to ask you for the 100th term? Do we want to jumpity-jump-jump there?
That would be
Yeah.
280.
No,
298.
we're going to go back to that a sub n formula and say, Steve, we don't want to jump 99 times from the first. Instead, we'd much rather just plug in 100 and say 3 times 100 minus 2, which would show us what would happen if we jumpity-jump-jump, which would be 298. Which would be 298. Okay, you got there. Okay. So, for or with an nth term formula, you can plug in, but that is not the only way to think about a sequence. You can also think about sequences with patterns in between each of the terms. Now, how would we write this sequence? With commas. 1, 4, 7, oops. My mouth is working faster than my pen. 7, 10, 13. How would we show 298? Would that go next?
Dot, dot, dot.
Nope, we would show a dot, dot, dot. And question. Theoretically, couldn't this sequence go on forever?
Yep.
Oh, that's kind of cool.
Couldn't it go on forever both ways?
Yes and yet no. We usually don't talk about negative first, negative second terms. Does that make sense?
Yeah.
So in that context, we always have a beginning for a sequence. But in a broader context, if you're thinking about different patterns, it could be possible to go over it. That'll make it. Okay, so we're gonna do that. Let's keep going. We've kind of already introduced the idea that maybe there's more than one way of defining sequences. There's more than one way of defining sequences, meaning they could give us an a sub n formula for the nth term. And then we could say f of n, if that helps. Just think of it as a function in terms of n. The last one was 3n minus 2. It's a function, just it has an n instead of an x. So you can give us an nth term formula, or we can just plug in n is 1, n is 5, n is 10, n is whichever term they want, the first, the 5th, the 10th, etc. But they could also give us a sequence and make us work for what to do. They could just say, hey, here's the A1, the A2, the A3. Maybe if they're really, really nice, they might even show you the AN somewhere down the line. But more often than not, they give you this and say, hey, figure out the pattern and you use the pattern. Sorry, for some reason my iPad and or Wi-Fi and or computer is being yeah, ignore it, it's blinking over there. It just wants attention.
Yeah, it's like me.
Like all of us at some point. Sometimes that's what makes believing in God the hardest. We want attention and we feel like we're not getting it. Deep thought. Okay, keep going. So, you guys got it? Let's go work with sequences that are given to us different ways. We already did an nth term one, where we could plug in n is 1, n is 2, n is 3. Let's go work with one where they give us the sequence. Let's go work with one where they give us the sequence. What if you're given 0, 3, 8, 15, 24, dot, dot, dot. Now, this example is one of the hardest things about sequences that, thankfully, I am not going to really expect out of you guys. At least not too much. And not without a context. This one says, here's some random sequence. You go figure out a formula for a sub n. This, yeah. Think really hard and hope that you can figure out patterns. That's hard. Yeah, don't worry.
That's it?
Don't, yeah, well, I'm not sure if it is the right way of putting that.
There's no hint, there's no clue.
Yeah, no.
Formula?
Mm-mm.
You just have to be smart.
Kind of. Not smart. Pattern finders. Not even pattern finders. Formula finders. It's rough. Now guys, hold on, wait one more time. I said this is one of the most difficult things about sequences. Like Calc PC, it was one of the things they hated the most when they got the sequences in series because they actually had to make up some formulas. That's when I expect you to be able to do it, not here. Alright? However, I'm still going to talk through it just a little bit because I still want you to realize you might be given sequences, it just won't be quite this hard of a problem. Now, hold on. What if I was to ask you for a sub 6 and a sub 7? Before we ever get near an a sub n, maybe we should think about an a sub 6 and a sub 7. Why did I choose those two, the 6th and the 7th terms?
Here's the next one. Go.
What do you have so far?
1, 2, 3, 4, 5.
You have the 5th term, and the 4th, and the 3rd, and the 2nd, and the 1st. So if you can figure out the pattern, which isn't always necessarily what the formula is, but if you can figure out the pattern, well, at least you can work with the sequence. So question, what's the pattern? Has anybody found a pattern first?
Oh, 5, 7 plus 9 plus 5 plus.
There you go. Sometimes just because you're smart in the academic GPA sense doesn't necessarily mean you see this fast.
Nope.
Others might beat you. But long story short, yeah, good job. Those who found the pattern. This isn't really something to memorize, it's something to see and puzzle through. You add 3, you add 5, you add 7, you add 9. People who are able to find the pattern, sweet, follow it, and what would a sub 6 be?
35.
Good, you would add 11 next, right?
Mm-hmm.
And from that 35, what would you do to go another step?
48.
48.
Oh, 48.
13, which would be 48. Now, hold on, pause. People who were like, hey, that was kind of fun finding the pattern. You might be a good computer programmer. You might not see the connection. Hopefully you see it a little bit later in this chapter. But long story short, if you're able to think about a pattern, maybe you're able to discuss the pattern. And you could tell a computer to repeat that pattern lots of times, and it could do it fast for you. Like a little own personal computing slave.
Yeah.
If you learn how to program and talk to it and make it do things. Now, coming on back.
It's like in the computer room.
This pattern, or this finding of terms, is called recursive formulas. And we're going to talk about those on the next page. And this is a lot of what programming is. Having a computer, now don't worry, we'll get back to it. Hold on, pause it right down. Having a computer do the work for you, but you figuring out what work you needed to do. But wait, our job was not just to find a 6th or 7th term. And if you could write a computer program, you could say, hey, continue the pattern, and the computer could find you a sub 100 or it could find you a sub 1,000. That'd be cool and all if we were all computers or programmers. But here's the dilemma. They didn't ask for a program for how to make a computer find bigger and bigger terms for us really, really fast. They said, we want a formula for a sub n where you take an n, wait a minute, n is 1 in this one, n is 2 in this one, n is 3 in this one, n is 4 in this one, n is 5 in this one. You take the actual n's, 1 and 2 and 3 and 4 and 5, and you plug in, and it should give you the numbers 0 and 3 and 8 and 15 and 24. Wait, you can't jumpity jump the pattern? Nope. You plug in 1 and get out 0. Well, how do you plug in 1 and get out 0? I don't know. What if we were to say n minus 1? Hey, you plug in 1, you get out 0. Cool. How about the next one? Plug in 2 and get out 3? Does n minus 1 work for everybody? The answer is no. What's another way to get out 0 from 1? N minus...
3n minus 3.
Oh, 3n minus 3? Let's try that. 3n minus 3. Plug in 1, you get 0. Plug in 2. 3 times 2 is 6. 6 minus 3 is 3. Hey, it works for 2. Plug in 3. 3 times 3 is 9. 9 minus 3 is 6. E for effort, but it's not 8.
F for failure.
It's a really hard pattern. Some of you might even try doing something cool like start at 0 and then try to talk about the odd numbers. If you talk about 2 times n minus 1, well, that's not going to work. If I plug in 1, I do end up getting 1. If I plug in 2, I end up getting 3. If I plug in 3, I end up getting 5. I kind of start getting these. But guess what? It's still not going to work.
Plus, but if you put 3 with a 0,
Oh, maybe put 3? Oh, but I don't want to add for the first term, do I?
No, because you want to get a 0.
Ridiculously
I could do negative 1 maybe.
Yeah.
Negative 1 plus plug in 1 would be 1, that'd be 0. Plug in 2, that'd be 4, 3. Negative 1 plus 3 would be 2. Did anybody find another pattern that has nothing to do with odds and nothing to do with addition? Okay, awkward
Wait.
silence. JJ.
I found one that works for everything except for the 0.
Uh-oh, what'd you find?
2n plus 1.
But 2n plus 1, let's see, plugging in 2, 2 times, well, plugging in 1, 2 times 1 plus 1 is 3, 2 times 2 is 4 plus 1 is 5. Still doesn't get me that 8 though, or that 24, that's just going to get me odd numbers. It does get you the pattern, but it doesn't get you the actual numbers. Has anybody seen yet how this can get hard?
Yes.
Why don't I give you the nth term formula then and see if it makes sense, even if you weren't able to come up with it.
Tyler, you were right. Oh.
Does anybody notice that 0, 3, 8, 15, 24 is awfully close to 1, 4, 9, 16, 25?
Of course.
One away from all the perfect squares.
Oh.
Ah, struggle enough. Wait, was there a fairly easy pattern to figure out? Yes, and it worked great for a little while. Yes. But is there a seemingly completely unrelated pattern as to how to get the terms separate from adding to the previous? And the answer is yes. Now, once again, I am not testing you on whether or not you can look at a sequence and come up with an nth term formula unless it is a very particular sequence in a very particular category called arithmetic or geometric, which we'll cover in 9.2 and 9.3 separately. And there are formulas to memorize, very specific special patterns to see that lead us to those formulas. However, I am going to expect you to kind of understand this whole recursive idea and how to use an nth term formula. So, let's go talk about this recursive idea. And this is actually what the SEQ mode is talking about in your calculator that you guys just put in a second ago. I'll give you a second to write it down. Recursive is, if you want to think about it and put it in like a little off to the side quotation marks, it's the jumpity jump jump one. It's the pattern way of working with a sequence. Finding a pattern and using it to jump to the next term, and then the next term, and then the next term. And if you can computer program, you can have a computer do as many jumps as quickly, well not as quickly, but much quicker than you could. Because the computer is doing just repeated or repetitions. I'm boring for the computer, it's boring. But also think about how you guys loved using RREF last chapter. How is that done? With recursive programming. Because you put in a certain pattern, a certain systematic approach, and you tell the computer or the program that you're making, you instruct it to do these same steps over and over and over and over and over and over to whatever size matrix you give it. Which is a little different than a sequence, but it is like a sequence of events. You're having the computer repeat a process over and over. Now, depending on maybe what's been given, what the input is from the user. That's when you set parameters in your programs, etc. And there are lots of places that computer programs can go wrong because there can be breaks in the code, and it's just a struggle everywhere you look. But anyway, cool stuff, but not for today. Recursive. What are pros? Pros are, long story short, patterns are easier to find. Number one, patterns are easier to find, and number two, can be used for small values of n. In the last page when I said find a sub 6, a sub 7, no big deal. The n's were small. Just kind of jumpity jump to the 6 and the 7. When I say n is 100, you're like, I don't want to jumpity jump to the 100. In the calculator, if you try to jumpity jump to the 100th, you have to keep track. You'd have to make sure that you count your steps, and it'd be annoying. Good thing computers were invented. But anyway, cons. It's annoying. It's bad for large values of n. So once again, the pros, easier to find, it's much easier to find patterns than it is to find a sub n's. And if you find a pattern, you can repeat them for very small values of n. Just like, oh, jump to the next term, jump to the next term, jump to the next term. But, that was to a pi, it didn't mean to be a pi, it meant to be a star. Bad for large values of n. Now here's an example of a recursively defined, ooh, this is sounding snazzy, a recursively defined sequence down below. A sequence can be given as just numbers separated by commas, and it's like, hey, you use it, you figure out the pattern, you keep going with it. A sequence can be defined with an a sub n, an nth term formula. You plug in n is 1, n is 2, n is 3. But a sequence can also be finally defined in a recursive manner where you are given two things. You're given two things, where to start and how to proceed. You're given two things, where to start and how to proceed. Now I do need you guys to add one quick thing in. There's one notation I couldn't get I don't know if I put it in wrong, I don't know. Something's funny. That needs to be a k minus 1. Change that real quick. That needs to be a k minus 1. Makes a big difference. Now, as you guys do that, I'm going to go ahead and quickly get my calculator. And some people that finished or were working on their tests didn't know what we were doing. We're in our calculators. We're in our mode. We have gone to SEQ. Dun, 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 dun. In function mode, this little variable button does pop out x's, but in SEQ mode, this function does pop out, ooh, I have lots of cool things written. That's actually how to tell the computer to generate the Fibonacci sequence. That's fun.
What?
But we figured out right now if you hit this button, the variable one, it pops out an N. Well, that's cool. Okay, anyway, coming back. A sub 1 is 14, that's where to start. A sub k says how to proceed, and here's what I mean. If I wanted to use this formula to proceed to A sub 2. Question, does A sub 2 equal A sub 1? And the answer is, no, they're different, right? Okay, could I use this formula to find A sub 2? Well, I guess so. There's a variable there, right? So I can say k is equal to 2, and then I can plug into my formula. And my formula would say negative 2 times a to the, plug in your k, right? Who is k? 2. And it'd be a sub 2 minus 1. And what would 2 minus 1 be? 1. Oh, wait a minute. What do I know since it was given to me? I know to start at 14, so I take 14 and say, hey, I'm going to multiply you by negative 2, and I get negative 28. That is a sub 2, or the second term. First term, 14. Second term, negative 28. What if I wanted to use this recursive idea to get to the third term? Now k is 3. I say, okay, fine. Using the formula from up above, a sub k, or a sub 3, is equal to negative 2 times a sub 3 minus 1, which would be a sub 2. A recursive formula always has you looking back. Always has you looking back, taking the previous term and repeating a pattern to that previous term, aka jumpity jump jump. The next term would be 56. Abby, can you take your Maddie's notes? Alex and other Maddie, if I can see your notes just at the end of the class. Now, if I was to write this, kiddos, we can keep going all day on this, A4, A5, A6. But at the end of the day, you would have 14, then negative 28, then 56. Have you figured out the pattern that this recursive formula is showing? Multiply by negative 2, multiply by negative 2. How would I go to the next term without writing all the notation? Just multiply by negative 2 again, right? And I would end up with negative 112, and I could keep going that way. So a recursively defined says, okay, you don't need to know the nth term formula, just tell me how to proceed. Tell me where to start, and tell me how to proceed. So, we're going to have to pick up tomorrow with the Fibonacci sequence, but for right now, let's just see if we can put this formula in our calculator. Okay, this formula in our calculator. N min, well, n is the variable, min means the minimum. Well, what's the first n that we're going to be using in a sequence?
14.
What's the first n we're going to be
Come on,
using?
you guys.
Oh, be nice. The first n, 1. The first n, 1. Remember, n is the placement. For the first term, second term, third term, n is the placement. So the first n will be 1. Now, hold on. If n min is 1, u of n, that's like a formula? What's u of n min? Well, who is n min? No, not quite. N min is 1. What's u of 1? Now, u is like an f of. What's f of 1? Well, f of 1 is the function at 1, and the function at 1 is the first term, and the first term is... So it writes it in a little bit different order than we do. We usually start with where to start and then how to proceed. It says how to proceed from where to start. That's what the computer, like the programming in your calculator does. So u of n min is the specific starting point, which in this term is going to be 14. Then up above, u of n says, how do I proceed? What formula or process do you want me to use? Well, we need to say, hey, negative 2, this is time for the formula now. Negative 2 times, have you guys noticed instead of A's, what are they using?
Use.
U's. U's and B's and W's instead of A's and I guess B's and C's, I don't know. Whatever. Has anybody found a lowercase u somewhere that we can write?
Second 7.
Second, number 7. There's a lowercase u. Number 8, there's a lowercase b. Number 9, there's a lowercase w. It's specifically for the sequence mode. Negative 2 times u. Which u do I want? Which a do I want? U of, but instead of k's, you guys see what they're using? N's, right? So it's going to be u of, calculator knows function notation, n minus 1. So there's a few things to change when you're using this programming in your TI calculator. Instead of a's, it's using u's. Instead of k's, it's using n's. Our book just uses k's to let you know, hey, this is recursive. But wait, how can we generate this sequence? Table.
Oh.
Hey! I know, I have 1, 2, 3, 4, 5, 6 already in my table. You might have something different, but first term is 14, second term negative 28, third term is, now why is this so cool? Because kiddos, what if I want the 100th term? What's the computer going to do or the programming going to do? Jumpity jump, jump, jump.
Jump.
99 times, and it says, hey, cool, it's negative 9 to the 30th. Wow, that's huge. I wouldn't want to do that myself. All right, go kids, maybe you can start chapter 9, section 1, homework number 33. But that's on Monday. Bye, guys.